So, hi everyone, I am Alessia, and today I will going to share with you some practical tips and tricks from training neural networks in an effective way. But before going into details, I wish to recall you some basic concepts behind neural networks. So, neural networks, in a nutshell, fundamentally, neural networks are nothing more than special and really good function approximators. You give it an input vector, and it performs a series of operations, and it gives out an output vector. And to train neural network to estimate an unknown function, you feed into the network data points, which we denote the training set, and that the network will learn from to make future predictions. This is what a neural network looks like. Every cyclical is a neuron, and the connection you see between the neurons are the weights. And each neuron has a set of weights, one for each corresponding input. And neural networks are composed by layers, and each layer is composed by neurons, one or more. And each neuron computes an output or activations, and the data passes through the network layer by layer until it reaches the last layer, and the activation of the last layer are the actual predictions that the network makes. But for a moment, imagine you have only one neuron with only two weights, only two inputs, so two weights, W1 and W2. In the plot on the right, you can see along the x-axis the W1 weight, along the y-axis the W2 weight, and along the z-axis the loss. This is the loss surface. Our goal is minimizing this loss and find the set of weights which enables to reach the minimum loss. Could seem easy, but real life could be more complicated. And here we can have multiple minima. And it's not so easy computing all the derivatives in order to find out which is the global optimum. So we use an iterative algorithm called gradient descent. I only give you the intuition behind. So, but for a moment, imagine we only care about only a single weight. So we start with a random point on this surface, and we try to descend the hill step by step, trying to reach the minimum. And at each step, we're updating our weights following the rule on the right. So the new weight is the old weight minus the gradient, so the direction we found to be steeper, multiplied by a parameter called learning rate. And this process ends when you reach the minimum loss. It's worth mentioning that we usually perform a weight update every batch. But what's a batch? You basically divide your training set into splits in order to fit them into your network, and this is your batches. So the name changed a bit. It becomes mini-batch gradient descent. Our main objective so is trying to find and reach the global optimum and not stop training if we get stuck in saddle points. Because they are minima, of course, but not the minima we want. We want the best. We want the global one. So difficult? Yeah. You have to make several choices in order to have a trained network that performs so well. One of the first questions you can have when designing neural networks could be, what type of architecture should I use? How many neurons should I put? How many layers should I stack? And there's not a general answer. Even Joshua Bengio, a boss in the field, didn't give a precise answer. How can I estimate the number of neurons and layers? Very simple. Just keep adding layers until the test error does not improve anymore. Other thing you can do is adding more layers while not tuning the hyperparameters, but I'm not sure that it could be a useful approach to obtain great results. But what are these hyperparameters? Well, hyperparameters are your model's magic number. So the number you set before starting the training and the values that are not selected directly by the learning algorithm itself. And hyperparameter optimization is a powerful tool to enable to extract the maximum power out of your model, but of course only when correctly implemented. And by not explicitly setting any hyperparameter, you're implicitly trusting the default hyperparameters that the developer of the model set. So this could be completely wrong for your problem, you don't know. Of course, the biggest mistake in hyperparameter optimization is not performing hyperparameter optimization at all. And if you're not performing hyperparameter optimization, you should start now. Well, this is a very rich but not exhaustive list of hyperparameters. You can see learning rate, weight decay coefficient, dropout rate, batch size, and so on. There are many, and the choices you can make are even more. And probably for some of them is enough picking a default value suggested in some paper, but still remains several choices to be made. You might be thinking that neural network training is an art. Indeed it is. And there are some techniques to automate this process, so it's not recommended to do manually, since you are the optimization method, and you are more likely going to fail this task. Not always okay, but you can address your goal in an automated way, performing grid search, for example. You basically set a search space and for your hyperparameters, and you select the values you want to try, and then you try to train your network using all the combination of these values. Doing this, you can leverage on parallel computing and train several models at the same time. Of course, the cross product of these lists grows exponentially with the number of hyperparameters. So this approach suffers from the curse of dimensionality, and it's not even guaranteed to find the best solution. Other thing you can do is a random search that is proved to is more effective, since you can obtain with 95% of probability the best solution within the 5% optima in your problem, with only 60 iterations. So let's talk about the learning rate, which is considered one of the most important hyperparameters to tune. The typical values for a neural network are less than 1 and greater than 10 to minus 6, but you shouldn't take these values too strictly. A possible question you can have is, should it keep it constant or should be variable? Well, often it's useful decreasing the learning rate while your training progresses. But say that, another question you can have is, should I use an adaptive gradient learning rate method or a learning rate schedule? What's the difference between them? Keras provides a rich set of adaptive gradient descent methods ready to be used. But it's not the main purpose of this talk, showing you the details about and the difference between them, but you can refer to the Keras official documentation for any further information. A useful insight you can read it almost everywhere is when the validation loss stops improving, decrease the learning rate. Okay, but how much? So for example, you can use a time-based learning rate schedule. So every epoch, the learning rate is decreased by the given amount. Keras has this type of schedule built in. And specifying the parameter decay, you can obtain the behavior described before. Otherwise, you can use a drop-based learning rate schedule. So the learning rate is decreased every a number specified of epochs. Keras doesn't provide this type of schedule built in, but you can use you can write your own using the learning rate schedule callback. And when fitting a model, well, as described in the snapshot. A very useful insight I found out following the online course Fast AI as an international fellow taken by Jeremy Howard and Rachel Thomas was this technique called cyclical learning rate. Basically, it eliminates the need to tune the learning rate and achieving optimal classification accuracy with no additional computation. Basically, you set boundaries within your learning rate can vary and step size, which is the number of epochs that you use to reach from base LR, the max LR. And as you can see, it follows a triangular fashion. As you can see in this plot following the red curve, you can obtain the same accuracy at the half the epochs. Since you're spending less time to train your network, it enables you to train bigger networks, of course. And here you can see the implementation. This comes from a pull request to Keras contrib, which is a repo that contains other Keras functionalities that are not yet added to the core of Keras. And now let me introduce you another super important hyperparameter, the batch size. And before, when I was talking about gradient descent, I said that we use mini batch gradient descent. So the weights update is performed after each batch passes through the network. But how this size should be big? Is there a rule? Well, not really. But we normally choose the batch size between 1 and, of course, a few hundred, as long as it fits in your memory or in GPU. The impact of your batch size is mainly computational. Higher the number, faster the computation, because there are less weight updates per epoch. So our desire is achieving the highest performance while minimizing the computation time. A paper published in November 2017 shows that batch size are strict correlated with the other super important hyperparameter we said, the learning rate. In particular, Leslie Smith said that you can obtain the same learning curve on both training and test set by increasing the batch size during training instead of decaying the learning rate. This approach reaches equivalent classification accuracy after the same number of training epochs, but with fewer parameter updates. Diving into details, when the learning rate drops by a factor of x, you increase your batch size of x, keeping the product of batch size and learning rate constant. So they're basically saying that you can use the learning rate schedules and convert it to increasing batch size schedules. In particular, they found out that it's possible increasing batch size during training until it reaches the number, the training set size divided by 10, and then go back to decaying the learning rate as usual. We saw how to boost our accuracy, but is very important during the training of neural networks, monitoring both the training accuracy and the test and the validation accuracy. Because they say to us very important thing, especially the difference between them. And we could see very high training accuracy and then become happy. But if you don't pay enough attention to both accuracy, we could incur in overfitting. And overfitting refers to the phenomenon which happens when you have a too capable model trying to fit too simple or too noisy data. And we can find that our model is overfitting when it is able to perform incredibly well on the training set, but poor in the test set. We don't want the best model for your training data. We want the best model for the real world, of course. So early stopping is the most commonly used form of regularization. It basically refers to the concept to stop training before convergence to avoid overfitting. So first of all, you need to split your data set in training set and test set as usual. Train your network only on the training set and evaluate the error on the validation set. One in a while. For example, every fifth epoch. Simply, you stop the training as soon as the error on the validation set is higher than when it was checked. You will use the weights of the step before as the result of training. But real life is a little bit different. Could seem easy. Because you are estimating your generalization error using only your test error. And often it doesn't evolve so smoothly. So we can't apply directly this approach. We now need a rule that tells us how and when stop training. And this stopping rules is called stopping criterion. But before introducing you the first stopping criterion, I'd like you to give the definition of a generalization loss. Basically, it is how much the current validation accuracy higher than the minimum validation accuracy we found so far. And high generalization loss is one obvious candidate reason to stop training because it directly indicates overfitting. So the first stopping criterion is what I call threshold criterion because you stop training as soon as your generalization loss exceeds a certain threshold. However, we might want to avoid stopping if the training is still progressing very rapidly, because the author of the paper cited at the bottom says that probably overfitting does not begin until the training, until the generalization loss decreases only slowly. So here I'm explaining you the second stopping criterion they presented in this paper. And if we define a training strip of length k as a sequence of key epochs, you calculate how much was the average training error during the strip, and then you divide this number by the minimum training error we found during the strip. The result is called training progress. Then you take this number and you take the generalization number and you divide it by this training progress. And this criterion tells us to stop when this quotient exceeds a certain threshold. The third stopping criteria I'm going to present to you relies only on the sign on the changes in the generalization loss. It tells you to stop training if the generalization loss is increased in S successive strips. The authors suggest that when the validation loss has increased only once, but during the S successive strips, it probably indicates the beginning of the, the latest overfitting. This last approach is similar in what Keras implements. It essentially stops training when a monitored quantity, for example, the validation loss, stop improving within a number of patient epochs. And so by default, it monitors validation accuracy. But if you need more sophisticated criteria, you can implement your own using the callbacks. One reliable approach to improve performance on neural network is what is called model ensembling. You train multiple independent models, and then you average their prediction at test time. As the number of models in your ensembles increase, the performance typically improves. As in real life, consulting a bunch of experts before taking a decision is usually a good idea. There are several approaches to build an ensemble. You can take the same models and use different random initializations. Could be dangerous because the variety is only due to the random initialization. Or you can run an average of parameters during training. This is a cheap way of getting 1% of true or performance. And you can do it using the average layer in Keras. Or you can use cross-validation to determine the best hyperparameters and then pick the most, let's say, top 10, and then add these models to the ensembles. This improves the variety of the generalization, but has the danger of including suboptimal models. Or you can take different checkpoints of a single model. If training is expensive, you can take different checkpoints of a single model over time and using to form the ensembles. And at this time, average the predictions. This has the advantage that it's very cheap. This approach is presented in snapshot ensembles, train 1, get M for free, by Hang et al. We know that the number of possible local minima grows exponentially within the number of parameters, and modern neural networks can have millions. So instead of training M different models independently from scratch, we let SGD to converge M times into minima. And each time the model converges, we save the weights. We take the snapshot. And yeah, and we add the corresponding model to the ensemble. We then restart the training using a larger learning rate in order to escape from local minima. They use the cyclic cosine annealing schedule, in which learning rate is raised and then quickly lowered following a cosine function. In contrast to other traditional ensembling method, following this procedure, the time required to do these kind of things is exactly the same of training one model. In this plot, you can see in red the learning rate used in this approach, which is raised and then quickly lowered following a cosine function. At this time, we basically take all the snapshot and we average the weights. In this snippet of code, you can see the implementation of this schedule. It comes from Scarce contrib, so you can easily find it on GitHub following this link. Now, let me introduce you Dropout. It's a simple way to prevent overfitting. But before delving into details, close your eyes and imagine this setting. We have a very little neural network, 2 layers, 2 neurons in the first layer, number 1 and number 2, that feeds into the neuron number 3. The neuron number 1 gives correct predictions on 80% of the time. The neuron number 2 gives always random predictions. So the best thing the neuron number 3 can do is take only the output from the neuron number 1 and suppress the neuron number 2. Imagine that the 2 orange neurons are really friends. They rely on each other. And the neuron number 2 is confident that the neuron number 1 will correct its mistakes. But we don't want that. We want that each neuron is able to perform a task by itself. So we then introduce Dropout in our network to kill from time to time neurons from our network. This will generate non-zero gradients for the neuron number 2, and the neuron number 3 is going to change this trivial function in order to better understand what's going on. And the combined performance should be likely be higher than 80%. I found a curious definition of dropout, as you can read here. Dropout, simply described, is the concept that you can learn how to do a task. While drunk, you should be able to do the task even better when sober. To be precise, if P is the probability that a neuron is kept, you randomly drop units with a probability 1 minus P during training. At test time, you don't apply dropout, and you keep all your units. The weights of the network at test time are scaled-down versions of the training weights. If a unit is retained with a probability P during training, at test time, the outgoing weights of that unit are multiplied by P. By using this scaling, 2 to N different networks with shared weights can be combined into a single network to be used at test time. So you can think a dropout as a form of model assembly. Since test time performance is so critical, in practice, Keras implements what is called inverted dropout. Here you basically divide by P the weights of some random units at the training time and don't modify the weights at test time. It is shown to be another way to achieve the same performance as dropout. To sum up, recall that when training a model, we aspire to find the minima of a loss function given a set of parameters. We can interpret the loss as the unhappiness of the network with respect to its parameter. The higher the loss, the higher the unhappiness. And we don't want that. We want to make our models happy. Thank you.
Thank you for the presentation. There will be many questions, I guess, so you can start. That's the 1, 2? Okay. No, that's too late.
So maybe that's a very paranoid question, but what is the limit?
Where are you? Okay.
Yeah.
Sorry.
What is the limit whereby using cross-validation in selection of models, we end up overfitting, even considering the cross-validation set. That is, in principle, you could run selection algorithm which always look at the cross-validation set, and clearly it would be like always looking at the test set. So there is a trade-off between always using your cross-validation set to train and actually repeat overfitting. I mean, if you do it automatically, you end up having overfitting. So you would need a third set. I mean, if, or is there some obvious way why I'm wrong? That's the question.
I'm not sure I have understood the question.
So cross-validation, in principle, allows you to say, yeah, I train this model here, and then on a completely different data set, I see how it performs. Okay. It does not necessarily mean, and this helps me select the best model.
Okay.
Then it makes a lot of sense to use it in this way. Mm-hmm. But if you do it automatically, you end up selecting the best model for the cross-validation set and the training set.
Okay, you're right. Yes.
But again, you get overfitting for the two. So in principle, you would need a third model to validate rather than select.
You're right.
So maybe it's paranoia. I'm just curious about whether it's paranoia or there's something to pay attention to.
The main problem with these things, and you cannot say anything as a rule. Let's say I show you how to probably boost your performance, but I'm not sure that for your specific problem, for your specific data set, for your, I don't know, is going to work. That's don't ask me why, because nobody knows.
Okay, next question.
Thanks for the presentation. So my question regards the fact that there has been a lot of research on automatic hyperparameter optimization using Bayesian methods. And I don't see anything of that here. So I was wondering, are you aware that you can do better probably than random search? Because these papers like put some priors on the hyperparameters, and then they have a Gaussian process that optimizes them. And so you don't have to do anything. You just run the model, and it optimizes the hyperparameters and the parameters for you. So there are many, many papers about this. So do you know them, or do you plan to?
I was aware. Probably they are going to be my next search area on Google. So yeah, I was aware.
Yeah, and I'm also happy that there is someone from Trento, because I'm also from Trento. So.
Oh, fine.
Okay, so the next question was who? It was you? Ah, okay. So some other. Oh, come on. Why did?
Hi, and thank you. My question is about the snapshot ensemble.
Okay.
And my question is, in your opinion, what is the trade-off or the better result about having a snapshot ensemble with a cyclic learning rate instead of having different random points with a decay learning rate? What is the improvement of this method?
Because here you're trying to converge several times and trying to reach several optima.
Okay.
That can, how to say it, might be able to generalize better on a subset of a data set or another. And you try to find out a set of weights, so the average, that can perform well on all your data set. And using the cyclic cosine annealing scheduled for the learning rate, you can go into minimum and then escape and trying to find better minima.
Okay, thank you.
Are there any other questions? Somebody else? Nobody?
No.
Okay, thank you. Close enough. Wait. Okay.
Sorry, I have a question regarding this.
Okay.
When you cyclic cosine annealing, the question is, are you taking the snapshots in a smart way when you are near local optima, or it's random? It's not. If you take it every nth iterations, you're not sure that you are in a local minima.
With this approach, we take a snapshot every a number of epochs.
Okay. So you could actually use the annealing to find a local optima, but the snapshot is not taken in that point. So you're kind
right.
of losing the okay.
You're right.
No, I was just asking.
Si, si. Okay.
Okay. Are there any questions? Any other? For sure. Okay. So we are done. Thank you. Thank you.